To find an optimal move in a competitive environment, an AI has to project the possible consequences of its actions. Take chess as a benchmark. The game has a branching factor of roughly 35 and an average depth of 80 moves, meaning the resulting state space graph contains around 10 to the power of 123 possible nodes. A state space graph is a mathematical map containing every possible configuration a system can reach. That node count is vastly larger than the total number of atoms in the observable universe. Because an AI cannot physically compute every single one of those futures before the clock runs out, it requires a structured strategy to navigate the possibilities. This diagram shows a game tree, mapping the state space from an initial root position down to the terminal states at the bottom. Notice the alternating horizontal rows. Each level is a ply, representing a single turn taken by one player before passing control. Navigating this massive structure efficiently and extracting the right move without drowning in the data is the core computational problem of artificial intelligence in game playing. For two-player zero-sum games, the standard solution is the Minimax search algorithm. A zero-sum game is a mathematical representation of a strict competition where one player's exact gain is directly tied to the other player's equivalent loss. The algorithm assumes two perfectly rational agents. The max player attempts to maximize its own utility, driving the score as high as possible. The min player attempts to minimize that exact same utility, pulling the score down to thwart max. We only find concrete utility values at the bottom terminal nodes. Minimax computes values recursively, pulling these outcomes back up through the branches. When min acts, it evaluates its children and chooses the lowest value. Given 4 and -1, min selects -1. Standing one level above, max evaluates min's predicted choices. Knowing exactly how min reacts, max selects the path yielding the highest available guaranteed value. This block of pseudocode shows the formal algorithmic representation of this process. The max value function mathematically evaluates its options by directly calling the min value function, which in turn calls max value, creating an alternating loop. Minimax mathematically guarantees perfect rational play, but it possesses a time complexity of big O of b to the power of m, meaning the time required scales exponentially with the depth of the tree. Big O notation is a mathematical way to describe how the runtime of an algorithm grows as the input size increases. Because of this exponential scaling, the algorithm will choke on its own exhaustive calculations in any deeply complex game. To play competitively, the AI must search deeper into the tree, but it cannot afford the computational time to evaluate every single node. The solution is alpha-beta pruning. This is a mathematical shortcut that ignores useless branches in the game tree without altering the final minimax root value. The algorithm tracks two bounds. First is the alpha variable, which represents the highest utility value seen so far by max along the current path. Second is the beta variable, representing the lowest utility value seen so far by min. This tree diagram shows how those variables move. The empty brackets act as containers for alpha and beta, passing bounds downward as the algorithm searches depth first. As max discovers terminal values at the bottom, it updates its alpha variable to reflect the new guaranteed score. By tracking these worst-case bounds, the algorithm gains a running memory of its guaranteed alternatives. This memory is what sets the trap for our algorithmic shortcut. Imagine men walking down a new branch of the game tree, carefully opening nodes to evaluate their worth. Elsewhere in the tree, max has already secured a guaranteed value of 10. Our alpha variable is firmly set at 10. This equation defines the conflict. Min evaluates the first child and discovers a value of 8. Because min's purpose is to minimize, this parent node is now constrained. It can be 8 or lower, but never higher than 8. Switching to max's perspective, the logic dictates action. Max will never choose a path that yields an 8 or worse when it already holds a guaranteed 10 in its pocket. The pruning condition is met. Min has seen a value less than alpha. The parent root node would never choose this path. This algorithm block shows the exact mathematical action taken. The code terminates the for loop early and skips the remaining children. This state space diagram illustrates the visual consequence. The remaining terminal nodes, values 6, 9, and 4, are entirely grayed out, completely ignored by the search. There is a strict rule to this mechanism. Alpha and beta values pass down to children and across branches, but they do not pass back up to parent nodes. This slammed door of alpha-beta pruning effectively slashes the branching factor of the tree. It allows an AI to peer nearly twice as far into the future using the exact same computational power. However, the real world and many complex games are not perfectly deterministic. They contain randomness. To handle explicitly random elements or suboptimal opponents, we use a variant called Expectiminimax. Expectiminimax is an algorithm designed to evaluate trees where chance events dictate the transition between states. This diagram details the structural change. A third type of node, the chance node, is inserted between max and men's turns. Chance nodes cannot simply pick a maximum or minimum. They represent the whims of the universe, calculated using specific, explicit probabilities. This formula defines the mathematical resolution. To evaluate a chance node, the algorithm calculates the expected value. Expected value is the weighted average of all possible child outcomes, found by multiplying each outcome by its probability and summing the results. This isolated node graph shows the calculation in action. The 1/3 probabilities multiply the respective terminal values, 3, 12, and 9, to generate a single weighted average for the chance node above them. Adding chance nodes to the search space introduces a devastating consequence, an exponential explosion of branches. The time complexity balloons to big O of b to the power of m, multiplied by n to the power of m, where n represents the number of random chance outcomes per turn. Alpha-beta pruning is practically useless here. Because chance nodes require a weighted average of all their children, the algorithm usually cannot skip any of them, unless strict utility bounds apply. Faced with this computational wall, the AI relies on a final tool, the evaluation function. An evaluation function is a heuristic formula that estimates the strategic worth of a non-terminal state without computing the game to its end. Instead of mapping an impossibly deep web of chance, the AI stops searching at a fixed depth and applies the evaluation function to assign a mathematical guess to its current position. To operate in stochastic environments, an AI must abandon perfect deterministic foresight. It relies instead on expected values, heuristics, and calculated probabilities to execute the best possible guess before the clock runs out.